So hey guys, what's going on? I'm Hunter, and I'm one of the academic coaches at Dash Academy. There's I see some familiar faces. But we're hosting a free exam review for your class that's going to be tonight from 7 to 9 p.m., okay? I know Physics 1, right? You're going to have to take Physics 2. Let's get the stuff down pat now. I know I see a lot of pre-meds in here. Definitely got to know this stuff for the MCAT. And let's just start early with this, right? How do we sign up? Well, we sign up just with this link here. And just make sure you guys type in the right email. You can use a student email. You could use your Gmail, Yahoo, whatever it is. Just make sure you plug it in correctly, because we had some students that, misspelled their name or whatever the email is, and they just don't get the link, okay? Also, 5 minutes before the session starts, so around 6:55 p.m., you guys will get the link. If you don't see it, check your junk or spam folder, okay? But we're going to be hammering kinematics, 1D, 2D, Newton's Law, all the things that you guys need to know, okay? Good luck on your exam. I know it's a week away, but let's get it started early. Any questions, guys? Yes. Unfortunately, since it's free, it's a free event, and we have a partnership with UCF. It's not going to be recorded and sent out, but yeah, definitely recommend coming if you can. At least pop in for a little bit. Yes. Anyone else?
Yeah.
Awesome. All right, guys. Thank you and good luck.
But I'm gonna have to double check because that number wouldn't match that either. So stop at the end so I can look at the actual problem and look at the numbers more to get the time, because with the angle you got, it still doesn't quite work. Yeah. So I'll have to double check the numbers a bit more. All right. So, there is so many resources going into this week. Obviously, I got my office hours. I want to remind you all, so that's another one. Take advantage of it at this point. So I sent out announcements yesterday about the exam and all the details of it, and the resources that I made sounds like a very generous term. It's a very generous term. I mixed up the problem sets for you all, and I took all the top hat questions and I put them in one document, and I also mixed those up. So those are all made. Let's see, one day. Oh, I'm not plugged in. So I'm just navigating over to that so I can show you all where they're at. Remember, they're always in the that's the wrong cable. They're always in the Files tab. Everything goes in there, so it's in one nice, easy to locate place. I just have personal preference. As opposed to making a bunch of modules that you have to kind of click through, I just prefer to make it look like a computer where there's a Files tab and all that jazz. So, yeah, sent out an announcement about this, but if you go to test 1, this is where it's all located. There is the mixed problem sets. The way you're going to use these is after you've kind of gone through the problem set. This is all mixed up because the test is going to be all mixed up. So it's one thing to look at a problem and say it's 2D kinematics and already get in that mindset. It's another thing to have them all mixed up and not have a header that says 2D kinematics and another header that says forces. Basically, on the test, can you determine whether it's a kinematics problem, a force problem, or a combination of the two quickly? You do not want to spend a bunch of time just trying to determine what type of problem it is. Because kinematics problems all basically boil down to, like, there's a process for doing it. It is always the same process. Givens, missing, kinematics equations, that kind of stuff. Force problems, there's the process, same thing, givens, missing, but it has the free body diagram, F equals ma. You want to immediately have a sense of what type of problem it is. If you do not immediately have a sense of what type of problem it is, it's going to take you more time, which is obvious. And in general, it should take you only, like, after reading the problem, it should really only take you about 10 seconds to figure out whether it's a kinematics or force problem. Pro tip, if it says the word force in it, it's a force problem. That's pretty much the indication of which one it is. In a lot of ways. So, like this one, a coin is dropped from a hot air balloon, find the maximum height reached, kinematics. Like, it's talking about location and velocities. Great. This one's also kinematics. This one, find the acceleration of the system, find the tension in the rope. This one doesn't say the word force anywhere, but it's a force problem. Part B says tension, that's a force. 4, you got a roller coaster starting from rest, assume that friction be ignored. That's an acceleration. That's a kinematics problem. Like, this is how quick you should, like, maybe not that quick, but something like that. That's why this exists. And building on that, you know you're really going to be ready when you look at a problem and you already have a sense of what you're going to have to do to solve it. Without even writing your givens and missings, you already have at least a sense of what to do. How do you develop that? That takes practice. Like, that is not something that you can just, that takes a lot of practice to get to the place where you can look at a problem and immediately tell what to do. But that's why I say, like, you know you're going to be ready if you get to that place. If you already recognize, oh, there's vectors, I'm going to have to break things into X and Y components, like those kind of flags, stuff like that. So anyway, great, exists. The top hat questions are all here mixed up together as well. I recommend doing the PowerPoint one because this one has all the answers. The PDF and the PowerPoint have all the answers. But if you download the PowerPoint, then you can go to the review tab and you can click the button that says hide ink, and it hides all the ink in the presentation. And so that hides the answers, and you can go back and forth and all that kind of jazz. So like, oh man, where'd all the answers go? And then you hit it and wow, they pop up. Fantastic. There is also a test review posted here. Now this is from my 2048 class, but I will quickly show you all what it is, and I'll tell you what parts aren't relevant. And I just need to update this. I'll probably try to do that tomorrow. It's really, most of it's the same. So vectors and units, great. There's a summary. There's some practice stuff. 1D kinematics, that's the kind of bullet point of the topics that are covered. 2D kinematics, topics that are covered, random problems, recommendation. Circular motion, we didn't do it, so don't worry about the slide. Great, ignore that. Newton's first law, yay. Applications of Newton laws, yay. And then the other, again, circular motion, ignore. And the only other place I think calculus shows up is like in the 1D kinematics. It uses the word integral right here. No, don't worry about that. So I can update this in like 30 seconds tomorrow. But it's 95% accurate for you. 90, even more than that. So this is not going to be like, you do not use this necessarily, like this list of topics. It's not like you need to memorize these. Again, it's not a memorization thing. This is just, hey, here are the ideas. If any of these ideas sound weird to you, then you should spend some time thinking about that. But ultimately, how do you get better at physics? You have to practice. There's no getting around it. So practice both the conceptual questions, practice the problem set problems, practice the quiz problems, because quiz problems are just a synthesis of the two, all that good stuff. Rule of thumb, if you do all the problem set problems, and it might seem like a lot, but just as a prescription for success, if you have done all of those and you look through the top hat questions and you're good with those, if you're able to do that without having other resource, if you're able to solve these with only a formula sheet next to you, you're ready, you will do well on the test. That is the rule of thumb. I have yet to, pretty much, I never hear from people saying, I did all the problems and I still didn't do well on the test. I do hear that every now and then, but what I find when I work with students that fall in that population, when I talk to the students and actually work with them, I will pick a problem on the problem set and say, all right, go ahead and show me how you solve this, but they don't know how to. So something in the preparation went off, because ideally if you've done the problems, you should be able to do them again. That makes sense, hopefully. And again, that's not a knock on the individuals that fell into that camp, but it just means how you do these matters. If you have someone guiding you through every single step, or you have the solutions in front of you the whole time and all that jazz, no, you won't be ready for the test, because on the test you don't have all those things. So, it should be like, hey, I can look at these and I can do these, then you're going to do a good job. So, and I say well for me, the floor for that is a B. That doesn't mean, and the reason I say that, that's kind of what I can basically guarantee. Ideally, you should be able to get an A if you've done all these things. But at least you should be guaranteed to be in this class if you're doing all these steps, in my opinion. And the reason maybe not an A is just there's variations in how things go and tests and all that jazz. But I can almost guarantee the B if you have done all these steps. So that's that. Tuesday will be our review. Today we're going to finish everything, the last bit of things. The only things left, let me just double check this before I confirm that. Yeah, we'll finish up this pulley problem and then we'll jump into spring force. Spring force, whatever, isn't a big deal. Like I'll mention it and we'll kind of blast through it because I'm not going to have any questions about it. It's really simple. So you're not really losing out much. But our main emphasis today will be friction force and inclined planes. We'll knock those out. There's one problem for each. And that's where we're going to be putting inclined planes is where we're going to put everything together. It's going to have everything. Normal force, friction force, gravity, vectors. So that'll be kind of a good summary of all the things. So, without any context of this problem previously, let's see how much this problem made sense. How does A1 compare to A2 in the following problems? So this is the problem we started last time. I've got two blocks connected by a string, connected by a pulley. How does the acceleration of block 1 compare to the acceleration of block 2? Is the acceleration of block 1 bigger than block 2? Is the acceleration of block 1 less than block 2? Is the acceleration of block 1 the same as block 2? Alright, I'll wait like 10 more seconds. It's one of those either you know it or you don't kind of situations. Alright, 5, 4, 3, 2, 1. Alright, so again, this was something we actually needed for last class, so it's actually not new. And this was the whole idea that if two things are stuck together, they have to have the same acceleration. Whatever happens to one happens to the other. Like, they're stuck together. If one moves to the right one, the other's going to move down one. Like, so on and so forth. And so just jumping back actually a few slides to give you all a recap of last class. This slide kind of has everything you need to know when it comes to, like, the major points when it comes to forces. Draw a free body diagram. Sum of forces in the x equals max. Sum of forces in the y equals may. You have to build the equation. Force problems, I don't care what force problem it is, it's always the same process. But instead of looking at the formula sheet and saying what equation am I going to use, you build the equation. So that's the difference between kinematics. Kinematics, you have to choose the equation. This one, you build the equation. It is always a guarantee you're going to use F net equals ma in a force problem. Like I can basically promise you that. And then this last point was the one that we kind of finished with. If multiple objects are together, you should consider them together. In this case, if they're attached by a string, they're going to experience the same acceleration. And the mass is the mass of the whole system. So last class, we worked on that problem. And pulleys were a weird problem in that there's a little trick to it. And that was that we're not going to work in X and Y. First, like, we're not going to work in left and rights and up and downs. We're going to work in forwards and backwards to make it a one-dimensional problem. Even though this block 2 is going up, down. Block 1 is going left, right. If we think about it in forwards and backwards, it's so much easier to solve. You can totally do this problem in X and Y, but there's some subtle things to it that results in mistakes if you're not careful. And this one is, in my opinion, the easiest way, the most straightforward way. Jam them together, draw the forces that make it move forward / backwards, and then draw the ones that don't do that, the ups and downs in this case. So part B says find the tension in the rope. In our original free body diagram for this problem, tension doesn't show up anywhere in it. So how do you choose where to draw a free body diagram? Wherever the force that you want to find is actually located. So where does tension show up in this picture? I'll give you all like 20 seconds to see if you can come with the judgment call on where we should draw, what we should draw a free body diagram of, where in this picture to actually have tension. And there was two possible answers to this. There's two possible places you can draw a free body diagram and you'll get the same answer either way. And so I'll quickly kind of do both. So we're still going to work in forwards and backwards. It's just useful. I'll briefly mention what happens if you don't work it in forwards and backwards. You can make a mistake because it's a subtle thing. All right, so we can look at the free body diagram acting on this object because that one has a tension force pulling it to the right. So that's option A. Option A is draw a free body diagram of this object. So tension pulls it to the right. Let me rephrase that. Tension pulls it forwards. Again, I'll show you why that's so beneficial. You still have the force of gravity acting on it. You still have the normal force acting on it. Fantastic. The mass of object 1 is 4 kilograms. I'm just going to jot down that information. The mass of object 2 is 1 kilogram. And we have a new given because we found it in the last part of this. We found that the acceleration was 1.96 meters per second squared. And it's positive because it's forwards. It's positive because it's forwards. So we're solving for the tension force. How are we going to do it? The same way we solve every single force problem. Sum of forces equals ma. Like that should never even be a question of what equation you're going to use. What the question is how do I build that? F net equals ma. So F, sum of forces in the y equals may. Sum of forces in the x equals max. We'll do the y first. We don't need to, but it's just to get in the good habit of doing this because very soon we're going to always have to do both of these. So in this direction, we have normal force, which is positive. We have gravity, which is negative because it's down. It's not in the forwards or backwards. And it turns out, not surprisingly, the acceleration in this direction is 0. So, yay! What was the point of this? We find that the normal force equals the gravitational force in this problem. We don't need to know that for this problem, but for future problems, the normal force does not always equal the gravitational force. I do not want you to fall into that bad habit, because that's a really easy habit to fall into, that, gravitational force equals normal force, because it happens so often. That's only true if your acceleration in the y is 0. That's only true if your acceleration in the y is 0. We did lots of problems where that wasn't the case, the whole elevator situation. In this problem, that is true, but we will see cases where that's not the case. So, in the x direction, it's literally just force of tension equals max. And then we just solve this. Like, that's the one we're actually going to use in this problem. I did both just for funsies, but the reality is we're just going to say force of tension equals the mass of this object, which is 1, times its acceleration, wrong number, which is 4, times its acceleration, which is 1.96, and that equals 7 point something. $7.84, and that's my answer. Yay. Nice and straightforward. All right, that was one option. I'm going to show you all. You could have done option B. You could have drawn the free body diagram for the other object. Let's do that, and it's going to be the exact, let's go through the motions. Now, this is one where, again, you got to work in forwards and backwards. You need to, I say need to. If you don't, you can still get the right answer, but only if you're careful. So in this case, the force of gravity is forwards. Again, forwards and backwards. We're not working it up and down. Forwards and backwards. And tension pulls it backwards. So I'm going to solve it this way, and then I'll show you what happens if you don't solve it this way, and it still works as long as you're careful. How are we going to solve this? Sum of force on x equals max. So how to build that equation? Fg2 is positive plus negative F tension equals mass 2 times A. I'll put the mass 1, mass 1, mass 1. And then we just plug in M2 times G plus negative force tension equals M2 times A. Then we're going to put in numbers. 1 times positive 9.8. Let me just move that over. So the force of tension, that's going to be too many steps. I think that's going to confuse people. I always write like every single step on here, just so that if you all look at this later, you're not terribly confused. But when you're solving these problems, you're more than welcome to, you can skip steps as long as you don't think you're going to make a mistake. So like I show every single bit of algebra, even though if I was actually solving this, I might not show every single step on my paper. Moved it over. So force of tension is going to equal 1 times 9.8 minus 1 times 1.96. Plug that in your calculator and you will get, wow, it's the same exact answer. For every force, there's an equal and opposite force. However much the string pulls block 1, the string pulls block 2, the exact same amount. It all works out. Doesn't matter which option you picked. Yeah.
So why for the M2 block is it pointing like, are the arrows like left and right?
Forwards and backwards. So we're not working with up and down. We're saying if you're pointed forwards, we draw it to the right. If you're backwards, we point it to the left. So that was the mindset we used to do this problem. As we said, it's a 1D problem where it's not left and right is, we're not going to say left and right is X and up and down is Y. We're going to say to the right is moving forwards, because moving forwards is moving along this path.
I thought we were drawing like M2.
We are, but in M2, does gravity move it forwards or backwards? So we drew it forwards. And then which way does tension pull it? Backwards. So I'm immediately going to show you all that you could do it in X and Y, and I'm going to show you the thing you have to realize, and if you don't realize it, you're going to get the wrong answer. And this is something that's like really, really subtle and really easy to make a mistake on. So I'll show it really quickly. So if instead you had decided, I don't like the forwards and backwards, I want to do up, down. So we're still going to do object 2, and you decide, I really like up, down so much better. And you draw this picture. Totally fine. You build your equation, sum of forces equals MA. This time we're in the Y direction. No problem here. Force of tension is positive. Great. Force of gravity is negative. Great. Equals M times A. And then you start plugging in all the numbers. So force of tension, just to move things around, equals MA plus M times G. Remember, FG is M times G. Just kick that over. Great, you're going through this process and you start plugging in numbers and you plug the mass of that as 1. You say, oh, I found my acceleration was positive 1.96. And then I put this 1 here and I put this 9.8 here and you spit out an answer. You'll be wrong. Can you spot what is incorrect about this? What we need to fix to make this work? Yeah. It's not the 9.8 that should be negative. That one's actually fine, but good guess on that. The 9.8 is positive because we decided gravity was negative here. So we're good. Like we already did the negative, but that was good. So it's not that.
Is the 1.96 in the X direction?
So in this case, we decided instead of going forwards and backwards, we're going to work in traditional X and Y. Up is positive, down is negative, to the right is positive, left is negative. So we went back to our more traditional way of viewing things. Anyone spot it yet? Yeah. It's not that. Good guess there as well. Force of tension, it's up, so it's positive. Which way is my block going to go? Up or down? What's my acceleration, positive or negative? You have to know that this should be a negative number. You got to know to put a negative sign there. When you found the acceleration in part A, it was a positive number. You then have to make the logical step that this is, if we're working in up-down, That's a negative acceleration. So this is why you want to work in forwards and backwards. Because what happens in this problem, if you work in traditional X and traditional Y, up, down, left, right, the acceleration of block 1 will be a positive acceleration because it's to the right. The acceleration of block 2 will be a negative acceleration because it's down. And so when you set up a bunch of things, you have to realize that they're opposite signs of each other. And that's a subtle little thing that's so easy to miss. And if you miss it, you get the completely wrong answer. Whereas if you work in forwards and backwards, you don't have to be, you just got to say, is it forwards or is it backwards? And that's so much easier. So, subtle little thing. If you do this, you will get the right answer that the force of tension now comes out to that value that we want it to be of 7.84. So, that's why I encourage you all with pulley problems, forwards and backwards. Just have that flag somewhere in your head. Pulley problem, I'm not going to work in up, down, left, right. I'm going to work in forwards and backwards. And that's the easiest way to avoid making a mistake. You don't have to, but then you have to be very careful with your pluses and minuses, and it's easy to get caught up on that. So, all right, spring force. Again, I'm going to mention it to you all. I'm not going to actually test you on it, not because it's hard. It's very easy. I just don't have haven't decided to put questions about it. Force of a spring is Kx. K is a spring constant. It's how stiff your spring is. The bigger the K, the stiffer it is. X is how far you displace it, how much you stretch it, how much you squish it. The more you squish it, the bigger the force. The more you stretch it, the bigger the force. That's the equation for it. Now, I'm actually going to slightly change this on the fly instead of X because people end up in, again, even though I'm not going to test you on it, I'd rather just be thorough. Let's say it's delta X because that's going to result in you making less, where we're going to call it the distance. Again, how much is it stretched? Not how big my spring is. Because if you have a spring, it's not guaranteed to have a force acting on it. And there you go. So we'll do one quick question about this, and then I'll jump into forces, friction. Because I really want to spend time more on that than inclined plane today. So I got to make sure that all fits. The spring has a spring constant of 50 newtons per meter, and it's stretched 1 centimeter. What's the force caused by the spring? Look, I'll even be so kind and give you all the equation. Wow, there it is. All right, we'll go 10 more seconds. And 5, 4, 3, 2, 1. So this problem is really just an exercise in, do you realize you need to convert units? This is my K, 50 newtons per meter. And this is my delta X. However, that is in centimeters. We do not like centimeters. Let me double check that this thing's running. Yay. 0.01 meters. Or however you want to write this. 1 e to the minus 2 or 0.01 meters. So we plug this in. 50 times 0.01. And you get 0.5 newtons. And there's our answer. All right, so be careful. Centimeters, again, you gotta convert your units. All our equations are tailored for base units. If any problem ever gives you anything that's not in meters, you need to convert it. Kilometers, millimeters, centimeters, all that kind of jazz. I'm not going to be mean and have a bunch of those, but there will definitely be at least a couple. I don't know how many, few, sprinkled throughout the test where are you being careful? And it seems silly, but it's just one of those, it's a skill that you got to be careful of. And so do that immediately. If you like, that's one of those flags that should pop up in your head. It's not in meters, and you immediately need to convert it. The second you see centimeters, it should make you feel uneasy, and you convert it. The way to think about this is as well, this newtons per meter literally says it takes 50 newtons to compress the spring 1 meter. That's what that represents. 50 newtons per meter. If I squish it 1 meter, it takes 50 newtons. If I stretch it 1 meter, it takes 50 newtons. If I'm stretching it 1 centimeter, I'm not stretching it a full meter, so I don't need a full 50 newtons. I just need a tiny bit. So that's what this, remember the more you understand about it, and I hadn't mentioned that, but this is a good example of that. All right, this problem I'm not going to give as a clicker question just for the sake of time. I really want to spend there's 2 problems I want to spend time on, and so I want to make sure we get to those. If you push the box on a frictionless surface with no air resistance, what would eventually happen after you stop pushing the box? Look at it, think about it, see if you can come up with the answer, and then I'll just mark which one. Would it stop? Would it speed up? Would it slide forever? Or who can really say? It would slide forever. Why? What is it missing? What slows things down? Oh, what a nice segue. Friction. So, friction is the force that makes things slow down when they're sliding or rolling. Sliding more traditionally. The variable for it is F for force with a little f next to it for friction. FF. The units are still newtons. And the equation for this, we do have an equation. And now we see why we spent so much time on normal force. To find the force of friction, you get the normal force. You have to do Newton sec F equals ma to find the normal force. And you multiply it by this coefficient of friction. This coefficient of friction is based upon 2 different materials. Wood on metal, or metal on metal, or pick any 2 materials between them. There's a big old table I'll show you. I do not expect you to have any of these coefficients memorized. I will either give you the coefficient, or the problem will say find the coefficient. So that is something either I give you, or I say solve for. It's not something it's not like gravity is 9.8 and you know the value of it. This value is incredibly complex you can only get it from experiments. You can't theoretically determine the coefficient of friction because literally it's due to all the bumpiness of things, and that's extremely, and the molecular forces and all sorts of craziness. If the normal force only equals the gravitational force if the acceleration is 0 and all that jazz. And the friction force is always opposite the direction of motion, which hopefully is like something you're comfortable with. I'm pretty sure I've already given you some problems related to that, even though I didn't teach you that, because it's what you expect. Friction slows things down. Just to get very, very, very briefly, why does friction slow things down? The easy answer is that everything's bumpy, and when bumpy things go over each other, they run into each other, and that causes stuff to slow down. Like, that's the really quick answer. Even on like a atomic scale, if you had something that was perfectly flat, it's still made of atoms, and atoms are like spheres, and so that's still a bunch of bumps. To get even more complicated, certain things like why is glue sticky and stuff like that, at some point it does get more complicated, where it's like the molecular forces, polar molecules, and all that kind of good stuff. We're not going to worry about that. For now, we're just going to say things are bumpy, and bumpy things slow each other down when they go over each other. All right. I'll spend the 2 minutes on this. I'll throw this one out to y'all. See what I say 2 minutes. I'll give you all like a minute to answer it. Give a guess. Is it harder to accelerate a box not moving or one that's already moving? Not moving, already moving, doesn't matter. The answer to this, I haven't taught you enough to actually know the answer to this. So take a guess. The answer to this will not be based on F equals MA, will not be based on anything like that. It's based on a reason that I haven't explained yet, so just give a guess. We are assuming friction. We just did a slide on friction, so yes, assuming friction exists. All right, we'll go like 10 more seconds. If you have an answer, just guess. And 5, 4, 3, 2, 1. All right. Again, I haven't taught you all this per se, but probably you might have guessed the right answer. It's harder to accelerate something that's not moving. You might have gotten that, might not have. Let's see. Yeah, most people. That's fine. Again, I'm not too worried about right or wrong. What's the reason for this? Again, it's not due to something I've taught you. The reason for this comes from the next slide. There is 2 different coefficients of friction for materials. There is a static coefficient. Static means not moving. So it's the one you get when things aren't moving, 2 materials touching each other. And then you have a kinetic one, and that's when they start moving. And these values are different. And the reason for this is not due to an equation, per se. Like, it's not an equation I can necessarily show you, or one that I even know. The reason for this is, I use my hands to describe this. Your hands are, if you like put your fingers together, your fingers are like bumpy. Like if you put your hands together and you kind of rub your fingers kind of, you like clapping and you put your hands together. When you're not moving, all the bumps can nestle into each other. All the little bumps can kind of nestle into each other and kind of get stuck. But once you start moving, you skate over those bumps. It's kind of like the difference if you're like going on a sidewalk and there's a big bump. So my daughter experiences this. If you go over a bump really slowly, it's like, you got like, it's hard to do. If there's a lot of bumps in a row, like those speed bumps that have all the little things, it's harder to get over it. Whereas when you're already moving, you kind of just like skate over the bumps. Another example is like in the ocean. If you're going really slow, you're going to go up and down every single wave, and you're like, whereas if you're going fast, you kind of like skate over the waves. So that's the idea. It's not really based on an equation per se. So that's static. They're all nestled together. And then kinetic, they're kind of lifted off each other and running over each other. And so it's easier. It's fun to know. I'm not going to ask a question like this in the test, but it's just there is 2 different ones, and you have to choose the right one if you're not moving versus moving. Again, I would either give these to you or say find them. All right. Don't worry about that one, but fun fact, the reason the tire gets pushed forward is static friction, not kinetic. It'd be kinetic if the wheel was spinning in place and sliding. If you lost traction, your wheel's spinning in place, that's kinetic. Static, you actually want your wheel to be stationary with respect to the ground. I'm not going to spend the time on it, though it is very interesting. Here's a quick table just showing a bunch of random static coefficients of friction, just to give you a sense of them. They generally go between 0 and 1. They can go over 1, but 1 is generally like the largest you'll see. The bigger the value, more friction, because you multiply it by a number. So the bigger it is, the bigger it is. It is kind of fun to mention that, in your body this matters. So fluids reduce friction. You don't want a bunch of friction in your body between joints. If they do a knee replacement and stuff like that, they're going to pick a material that has a lower coefficient of friction. A slippery material. You want your bones grinding against each other. That's a high coefficient of friction if they're grinding. So there you go. Again, you don't need to know any of these values. Let's do a problem that actually uses these things to see what it looks like. Suppose you have a wooden crate, 120 kilogram wooden crate, resting on a wooden floor with a coefficient of static friction of 0.5 between the 2 surfaces, the crate and the ground. What maximum force can you exert horizontally without moving it? And then we'll do part B. It says, hey, you get it moving. If you keep pushing it with the same force, what will its acceleration be? And then it gives you the kinetic friction. We're going to solve this the same way we solve every single force problem. Free body diagram. Always, 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 always. All right, try to draw the arrows. And we're going to assume you're pushing it to the right. Not that it really matters. If you want, you could push it to the left. You'll get the same answer at the end. All right, y'all tell me, what arrows should I draw? Gravity, always gravity. And it's down. All right. Normal, which way is that going to point?
Up.
Which is great for us because otherwise it'd be falling. Remember, you can always at any point look at your picture and say, does it match what's happening? All right, anything else? You applied, we're pushing it. Which way we want to push it? Sounds great. Applied force. According to this picture, it should be accelerating to the right. Why isn't it? Friction should be to the... It's not moving, but there's still friction. That's the reason it's not moving. I'm pushing it, and again, you can experience like, I'm pushing this desk. It's not moving. Why? Because friction's opposing me. Just because something's not moving doesn't mean there isn't friction. I mean, that's the reason it's not moving. So... Step 1, my mass is 120 kilograms. The coefficient of friction, the symbol for that is mu. It's a U with an extra tail. That's how you draw it. It has no units, and that comes from the equation. So FF equals mu Fn. The units of normal force are newtons. The units of friction force are newtons. I don't want to multiply it by another unit. So coefficient has no units to it. It's like the only thing we've learned so far with no units. So mu, and this is static, equals 0.5. No units, because it just scales things. And we can leave it there. There's technically another given that we're going to use at some point. But we'll discover what it is. Step 2. What are we solving for? What maximum force can you exert horizontally? Which one is it? Which force here represents me pushing it? It's the applied force. Applied force is a catch-all for any kind of like someone pushing something. Guess what equation we're going to use? Hopefully it's obvious. It's same one always. F equals ma, FMA, always, like every single force problem. It's not even, you don't even need to look at your formula sheet. It's always this one. Now, remember there's two of them, in the X and in the Y. In this problem, you need both. And if you do not do both, you can't quite, in fact, I'm going to do the Y first. You'll see why in a second. We have to build these equations, like every single force problem that's going to happen. It's a guarantee. In a force problem, you don't have to decide how to solve it. You just have to go through the motions, which sounds maybe easy, but you got to do a few of these before you get this skill down. All right, what forces are pointed up and down? Normal and gravity. Normal force, positive or negative? It's up. It's positive. Gravity, positive or negative? Negative. It's down. All right, and this is where we're going to discover, to save me space, what's the acceleration in the up-down direction? 0. My block is not leaving the floor. So this equals 0. So then if I just add the gravitational force to both sides, do a little bit of algebra, in this problem, the normal force equals the gravitational force. It's always good to go through these motions. Don't just assume they're equal. Make certain you know why they're equal if they are, because sometimes they won't be. In inclined planes, they won't be. So Fn equals mg. And you may, why did we do that? Let's build the next equation in the x direction. Which forces are pointed left, right?
Friction and
Applied force is positive, friction force is negative. If my block's not moving, what's its acceleration left, right? It's also 0. Again, I'm going to save myself a little bit of space by deciding that here. So that's going to equal 0. It only equals 0 because A is 0. Part B, A will not be 0. So FA, and we can put the equation for FF, so we are going to use that new equation. It's actually up here. I'll just highlight that. FF equals mu Fn. So we can chuck that in here. Fn equals 0. And then to do some more highlighting, oh look, we know the value of Fn. It's m times g. We had to find that out to actually solve the x direction. So when you're working with friction, you need both. So Fa plus negative mu mg equals 0. We're just going to chuck that to the other side, plug numbers in, and solve. So this is how you solve a friction problem. The same way we solve every force problem. Sum up the forces. Yeah, I really wanted to fit step 4 on this page, but I think I'm going to have to do it on the next slide. That's all right. Part B is going to need us to have this anyway. So we do the things. So FA plus, look again, I don't want to, I'm going to save myself some effort. We just add it to the other side. So step 4, FA is going to equal 0.5 times 120 times 9.8. And that's going to equal, I think, 58 point something based on my class this morning. Oh, see, that's my memory wasn't great. 588. There you go. It's the same process for every single force problem. And if you're looking at this and saying, great, looks super easy, again, try these on your own. If when you actually solve it's easy, that I'm really happy to see that. But I will say a lot of people I've seen watching me do this will make sense. When you try to start building your own force equations, that's when you're going to determine whether or not you really understand it. All right, that's part A. Part B, I'm just going to quickly jump back to this one, and then don't worry, I'll jump back to that slide. If you continue to exert the same force, once the crate starts to slip, what will the acceleration then be? So it's a continuation of this, where we're going to take those forces. So we're going to take that force, and now it's a given. So we're going to make a new set of givens and all that jazz. We're going to make a new free body diagram that's going to look just like the first free body diagram. So now my crate is moving. Oh, that one's the next thing I'm going to have us do. So we do a new free body diagram. Fun fact, the new free body diagram is the exact same with one small difference. The applied force arrow is bigger than the friction force because it's accelerating to the right. It's a small difference, but it was one of the questions on the quiz was, hey, a car is speeding up. It / is / was. I think it's on the quiz due this Saturday, maybe. One of the questions relates to, hey, car is speeding up. Draw the free body diagram, and the size of the arrows matters. Because whichever one wins, that's which way it's going to accelerate. And if you miss that, then yeah. I mean, if you don't realize that, you'll get the answer wrong. So mass equals 120 kilograms. My applied force, we know. We have a new coefficient of friction. It tells us that the coefficient of friction for sliding is 0.3. So I didn't just pull that out of my head. It came from the problem. That's that. That's what we got. Step 2, we are solving for acceleration. How are we going to find it? Sum of forces in the y equals MAY. Sum of forces in the x equals MAX. If it seems like tedious always writing these same things, if you skip any step, you are very likely, so there's no shortcuts here. Even if you do, like, if you try to skip any steps, you're secretly doing these steps. And if you're doing them like shortcuts, air quotes, that just means you're trying to do it in your head. You're doing steps in your head. And anytime you do steps in your head, you're likely to make a mistake. No matter what, this is how you solve these problems. There is no shortcuts here. This is the logic you're following. So we're going to build this. Yes, AY is going to be 0 again. So we're going to still find that these are equal to each other. But if you do not go through these motions, you risk falling into the bad habit that the normal force is always the gravitational force, and then missing a problem where that's not true, where the acceleration is not 0. So, better safe than sorry. It's better to go through the motions than skip a bunch of things and make a bunch of mistakes. So this one, applied force plus the friction force, which is negative, no longer equals 0. I mean, that's the whole, if it equals 0, then we're done. The answer is 0. And so my applied force plus negative mu m times g, for the same exact reason before, equals m times a. We're solving for a. So then we put in the numbers, 588 plus negative 0.3 times 120 times 9.8 equals 120 times AX. I'm just going to divide this whole side by 120. So that way, another tip I recommend for you all, if you get an equation where everything is on one side by itself, plug that whole thing in your calculator in one go and hit enter, and you're going to be way less likely to make a mistake. The more times you have to plug stuff in your calculator, every single time you have to hit enter is another time you can make a mistake. And if you've hit it like 5 times, it's really hard to track your mistakes. Whereas if you have a single equation that solves for it, so I'll put like parentheses around it. That is one thing you have to be careful of with these division problems. So I'm going to put 588 plus negative 0.3 times 120 times 9.8, all divided by 120. And I get 1.96. And I can look at the thing I plugged in my calculator, and I can look and see if it's what's written on my paper. It's another way of catching mistakes. So AX equals positive 1.96. I made a mistake this morning when solving this problem. This one or a different one, and I got a negative acceleration. And that was actually a flag for me that I did it wrong. Why would a negative acceleration be ridiculous? Which one's winning if I have a negative acceleration? Applied force or friction force? Friction force. And that's nonsense. Never are you going to push an object and friction is going to make it go backwards. So, if you know what your answer represents, this is positive. Makes sense. I push it to the right. Friction either makes it not move or just slower. It never makes things move backwards. That would be weird. Okay. So the good news, I got 27 minutes for this last inclined plane, and I wanted to give us time for this. That's why I've been kind of moving a little bit quicker than usual. I needed to make certain I got through everything by the end of today so that you have everything you need before we can advance. Inclined planes, the name of the game is an inclined plane is the exact same problem as this if you rotate your head, with a slight caveat. With a very, very slight caveat to it. I say slight, like one little additional detail. An inclined plane problem is the exact same as this if you turn your head sideways. There's one detail you have to do. So, let's do it. Draw a free body diagram for the following. Block on an inclined plane. There is friction. This problem is going to combine all the skills, which is why it's at the very end. And there should be 3 arrows on your picture. All right, what's the freebie? Gravity. Which way is it point? Always straight down. Gravity always pulls things down. I don't care if you're on an inclined plane, it's always straight down. Like, gravity doesn't care that it's on a plane. All right, what else? There is friction. Which way does my block want to slide? Down the hill, so friction is going to point the exact opposite direction. And then there's one more. Normal force. And this one's going to be the subtle one. Friction force is not straight up. Friction force is away from the surface. Always, always. Normal force is always directly away from the surface. It always points directly away from the surface. Like, period. That's always true. So, all I need you to realize here is that I can take this problem, and I'm going to copy and paste it for a reason. I'm going to take this problem, and it's just like the last problem if you just turn your head to this. Now, in this case, though, one of my arrows does not point left or right. So guess what we're going to have the pleasure of doing? We're going to make a triangle, and we're going to break it into X and Y components. Now, the reason we rotate it like this is either you would have to break the friction force and the normal force into components, and that's twice as much work. Or you can turn your head and just make gravity into its components. So you can either do, basically you have to work. Now, we're going to draw that by, we're going to find the part of gravity that points into it, and the part of gravity, so basically we're going to make X down the thing, and Y into / away from it. So that's how we're going to define things. So our Y component of gravity is going to be like into the plane, and then the X component is going to be down the thing. And you can almost pretend like this FGX is like the applied force in our last problem. And the FGY is kind of like our gravitational force and all that good stuff. And the only last thing that I need to kind of go through, and this is going to take a little bit, like I say, a little bit of time. In these problems, I'm going to give you this angle. And so you got to do some geometry. I say you have to do some geometry. Either you do some geometry or there's a couple equations you can jot down in your 5x8 note card. That'll be up to you. So, that angle, and I'll straight up tell you this, and then I'm going to let you spend some time and take your guess. That angle is either this angle here or it's this angle here. It's one of those two. I'm going to give you all 30 seconds to take your bet on which one you think it is. And there's a few ways you can logic through this. There's lots of ways. Geometry, you can use, I'll show you a couple different ways. I'll tell you the way I think about it, which is logically. Yeah, take your bet. All right, the grand reveal. And actually to explain it, well, yeah, it's this one. I'm just going to tell you it. That one's theta, which by extension makes this one 90 minus theta because they're right angles to each other. So I'm going to show you a couple ways you can logic that out. The first way is the way I do it. If we were actually on a flat surface, which way would gravity point? Gravity would point completely down if we were on a flat surface. What's my angle for a flat surface? It's 0. If you're on a flat surface, this angle becomes 0 because this angle is 0. When you're on a flat surface, gravity points completely down. So as your ramp gets flatter, as your angle gets smaller, this swings towards being the one that you expect it to be. And you can do the opposite logic as well. If I'm like completely vertical, then gravity completely will make you slide down. So that's the way I logic through it. When my thing gets flat, that angle gets small. So that's one way. The other way is going to be in this beautiful picture that's drawn without which one is it? So there's some questions here. These are just to help you kind of guide through this, but don't worry about it too much. I'm just going to put the answers here. You can look through them on your own. Great. So there's the picture. Here's the other way to see this. If this angle is theta, there's a right triangle. So that top one's going to be 90 minus theta. If that one's 90 minus theta, then this one is 90 minus theta. And you know, turn that into a plus theta. But so this is the other way to do it, is geometry. That's the easiest way to kind of show it. All right, why does this all matter? Why are we going through these motions? We always have to split vectors into components because at the end of the day, you got to sum up the x and sum up the y, like F equals ma. And when you do so, you know, let's just quickly do it just to show something. So if I take this thing and I rotate it, I don't think I can do that one actually. I'm going to do this one. If I take this thing and rotate it, so remember that's theta. Sum of forces in the x equals max. Actually, I'm going to do the y ones first because they're easier. Which ones are pointed up, down? Gravity. Sorry, not gravity, normal force. And that one. So you get that the normal force plus the negative FGY equals 0. Now, I will give you all a second to try this out because I think it's useful. I have a triangle. FG is the hypotenuse. I'll draw it over here to the side just to make it easier to see. FGY, FGX, that's my angle. Which one would you use? How would you find FGY? It's just good vector practice. If I want to find FGY in terms of FG, sine, cosine, tangent, think about it for a few moments. Go through SOHCAHTOA. Is it the adjacent side, the opposite side? All that good stuff. This is the adjacent. It's the one touching the angle. This is the opposite. It's opposite the angle. So if you all want to find FGY, and you can go through the motions, it's FG times cosine of theta. And FGX is going to be FG times sine of theta, just from trigonometry, to break it into components. Super, super important skill. So if we do that up here, we get that the normal force plus, and I set this equal to 0. Why? The acceleration, it's not flying off the surface. Same process we've been going through. Equals negative FG cosine of theta equals 0. So therefore, Fn equals Fg cosine theta, which is equal to mg cosine theta. Just going through the motions, doing all the trig. And this slide's a little bit neater. There you go. If you want the normal force, it's mg cosine theta because of sum of forces equals ma. If you want the x direction, it's mg sine of theta. If you all want the friction force, you got to chuck a mu in front of it. Chuck a mu in front of a normal force. So this is one of those things that you can either derive it yourself. These equations are not on the formula sheet because they're not new physics. Like, these are not new physics equations. This is just sum of forces equals ma and break things into components. But if you're like, man, these are really useful, I don't want to have to derive these, put them on your 5x8 note card. Choice is yours. I personally end up just deriving them whenever I need them. Like, as you do this stuff enough and this stuff gets really quick, you realize that's theta and you go through the motion. So whatever y'all are more comfortable with, do that. I do not have these memorized. If I want these equations, I derive them every time, which sounds a little tedious, but again, it takes, the quicker you get at this stuff, it doesn't take that long. At some point in this class, you all will look back and you'll look at problems that were really hard for you and you'll be like, oh, that's really easy. It will happen. It's like anything in life. When you first got behind, again, I keep mentioning the car. When you all first got behind a steering wheel, my experience at least was it was way more intimidating than I thought it'd be. When I first got behind this, you're in the car with parents and all that jazz and it's nothing. Then you get behind the steering wheel and you're like, oh, this is way more intimidating. And then as time goes on, it becomes second nature to you and you don't think anything of it anymore. And then driving gets really dangerous because then you forget that it's really dangerous. Physics at least isn't dangerous, but you will get to that point. You will get to the point where you're going to look back and say, hey, this problem used to be really challenging, and you're just going to go through the motion of the given and the miss, and it's going to be like second nature to you. It will start to have happened already, I can almost guarantee. It's the process of learning. And when you start doing this stuff, you can do it with someone who hasn't seen physics before, and you'll get to feel super smart and all the good things and all that jazz. But you'll get there. But when you first see it, yeah, it's not something you're used to. You haven't learned it before, unless you took physics before in high school. All right, so this is the last. I just want to solve a problem with this now, just to actually apply it and make sense of it. And that's the end of what I need to cover. Like, that's the end. That's everything that'll be on test 1. So machine at a post office sends packages down a chute and down a ramp. Calculate the acceleration of a box headed down a 10-degree slope, assuming the coefficient of friction for that package on a waxed wood is 0.1. And then find the angle of the slope down which this box can move at a constant velocity. I might not get to part B, but I'll post that worked out. If you all are in the labs, you had to do part B. Part B is how you found the static coefficient of friction. You can look back at that lab if you did it. So first step, shock and awe, free body diagram, always. And it's one we've already done, so I'm going to kind of zip through it. You got gravity going down. You got normal force going away from it. You got friction. It's the same one we've been using this entire time. Now, I didn't draw my picture beautifully. It's a 10-degree slope. It should be pretty flat. Through the magic of erasing things, I'll make it better. There we go. And this actually makes it a little easier. Oh, my normal force is trash now. It makes it a little bit easier to see some of these relationships if you draw the picture. Nice. This one's pretty flat, so it shows some of these things. This is 10 degrees. And if you all draw this, you can see that, oh, this angle is also really tiny. So you can also draw like an extreme case, and it helps you to see that relationship as well. So it turns out that this angle is 10 degrees. Just to point this out, a really common mistake people make when doing this triangle down here is they like to make this one the hypotenuse. They like to make the one in the surface the hypotenuse. That is not correct because this is the biggest, this is the hypotenuse. Like, it's got to be, you're breaking it into components. The components have to be smaller. Anytime you're breaking something into components, the two sides better be smaller. So, drawing that right triangle is a skill that trips people up. That happened a lot in my 2048 class, the engineering one. Okay. Write down our givens. We have the angle, and we have mu for kinetic. It's sliding, so it's kinetic. Even though it doesn't say that, we just know that. And that's it. No mass. There's no mass in this problem. We're solving for the acceleration. How are we going to find it? The same way we do all of these. It's like once you all get a few of these under your belt, it gets much, much easier. And, we're going to do the same in the x direction. Our acceleration in the y is 0. So just to remind you all, x is down the hill. So again, we've kind of done a creative thing with our coordinate system. You can do that. We rotated it. So we made y away from the surface into the surface. We made x down the hill. So it's not flying off the surface. Yay. That is another reason we did this. If you didn't do this and you worked in traditional up-down, it is awful. because now your left, right, you have an acceleration, and your up, down, you have an acceleration, and it's just unpleasant. This way, one of our accelerations is 0 by rotating it. How nice. So Fn plus negative FGY, because we're breaking things into components, because we're really good at remembering to do that, equals 0. Again, I'm just going to derive the whole thing again. FGY, reminder to you all, if we look at our triangle here, FGY equals FG times cosine of theta. FGX equals FG times sine of theta. I am not pulling those out of thin air. It comes from the geometry, SOHCAHTOA. We've done that so many times. I'll let you go through that motion. That's good practice for vectors to see why that is. If you're like, where the hell did those come from? Do SOHCAHTOA and find it. Discover that for yourself. Like, it's a really good exercise because it comes up in so many problems. So yeah, FGY equals this down here. I'll just highlight it. So Fn plus negative. Oh, and I'll make a note here. Fg is always mg. That's never going anywhere. Like that's. I'm just trying to save space at this point. Cosine of theta equals 0. Yay, we got our normal force. But the problem didn't ask about normal force. Why did we do all that? We're going to have to deal with friction. Friction deals with normal force. Everything's connected. There is no escape. All right, so don't worry. I'm going to copy all this. Oop. We're going to chuck it here. So we're going to build our x equation. So sum of force in the x, we have FGX, and I'm going to get rid of this arrow thing there because that's just going to confuse people, plus negative FF equals MAX. The acceleration in the x is not 0. That's what we're solving for, so don't make it 0. FGX is going to be, let's highlight that one, that's the yellow one. So that's just going to get chucked right there. FG is still m times g. So mg sine of theta plus mu Fn. Don't forget your negative sign. It's easy to lose track of those. Equals m times ax. Great, write it one last time. Sine of theta plus, I need a new color, orange. How awful is that? That's terrible. Pink. Yeah, that's acceptable. All right, that's going to get chucked into there. So you get negative mu mg cosine of theta equals MAX. And if that last expression looks like, man, what a gross expression. We didn't jump just to that last expression. We built it step by step by step. Every single one of you in here is capable of doing this. Like, I didn't do any wizardry. It was just a bunch of small steps. How do you climb a 100-story building? One step at a time. At the end, it's an impressive feat. But all the individual steps aren't that impressive. That's where I eventually want you all to get to. In physics, is realizing that and not being intimidated by a problem. One step at a time, and you all can do really complex, hard things. A hard thing is just something with a lot of steps. That's generally a rule of thumb in life. All right, something really cool. I didn't give you mass. Why? Because mass cancels. Every single term has mass in it. It cancels. Again, if you all did in the labs, you saw that you didn't care about the mass. This is why. Every single term has mass. If every single term is multiplied by 2, get rid of it. And then the final result is that the acceleration in the x is just g sine of theta plus negative mu g cosine of theta. And we're just going to plug, so ax equals 9.8 times sine of 10. It looks gross, but it's just a bunch of numbers. Don't be intimidated by an equation. It's just a recipe. Do this, then this, then this. And I can chuck that whole thing in the calculator, and I think this is maybe the one that I made a typo on. I think when I plugged this in my calculator in my first class today, I missed the decimal place or something on the 0.3, and I put 3 instead, and I got a negative acceleration, which is absolutely nonsense. But you can then catch that and then fix it. You're gonna make mistakes in life. It's just whether or not you realize it, catch it, and fix it. Like, again, another rule of thumb. It's okay to make mistakes. In fact, it's unavoidable. I don't care. No one's perfect. You're going to make mistakes. The difference between people that seem like they're perfect is they just might catch more of them. And case in point, I got a negative acceleration. Nonsense. Something went wrong. Funny how that all works out. Well, my mu is at -3. So that's one thing. So that was a catch. No idea where I got that negative from. The other one, just going to double check, cosine of 10, all that good stuff. There we go. I got a positive acceleration. So I got a negative acceleration because I literally put the wrong mu in there. Why did I put 0.3? Because a previous problem had 0.3. So my brain, that was a thing. How did I catch it? I got a negative answer, and that's nonsense. In that case, it would mean that this block just wouldn't move down the inclined plane. It wouldn't mean it actually moves backwards, but we know it's going to move. The whole problem says what's the acceleration. It's not going to be 0. So 0.737. No units, because it's mu. It's really small. Why? Because we're on a 10 degrees hill. Like, it's almost flat. 10 degrees is really, like, yeah, it's not going to slide down very fast. Yeah. Ooh, thank you. We're not solving for mu. There we go. Yeah, it should have units. Yeah, we're not solving for mu, so it should have units. I think it's great. Great catch. On the test, there will be some questions with There will be some problems that have answers with different units. So maybe the answer A is 70 newtons, answer B is 70 kilograms. Just look and notice of the same number and make the right choice in the unit. So, that's that. At this point, that's everything. There was one last thing I wanted to point out to you all for studying purposes. So yeah, my office hours, they still exist. Monday through Thursday. I assume Thursday I'm going to be absolutely packed because that's exam day and that's always how that goes. But the help room hours, this is staffed by people from undergrads that have taken your class. It's located in Physical Sciences building, same building as my office. Look at all these hours. 3 of these people, Robin was one of my previous students. Emelina was one of my previous students. Leo was my previous LA. Sophia is my current LA. They're great. All these people you can go to, except for Dr. Bruckner's office hours. That's another instructor. So many times, so many people you can go to other than me. Take advantage of it if you're having difficulty. Individual help will accelerate things for you. It can't do it all for you, but it can help a lot. It accelerates things, for sure. Have a good weekend, y'all. See you Tuesday, review day, all that good stuff. No cards, yada, yada.